You made headlines 10 years ago or so about showing where the photon went in the double slit experiment, which is supposed to not be done. As you mentioned, you can't say what the particle is doing prior to a measurement, only when you've measured.
That's right.
But what did you actually show?
Yeah. So I'm always a little worried about the wording of that experiment, what we did and why we did it, but I think it demonstrates a few interesting things. First of all, we can come back to this distinction between strong and weak measurement. Send a photon through a double slit. It's going to hit this screen eventually. But along the way, what stops me from measuring exactly where the photon is? In principle, I can do that. The problem is usually when we measure where a photon is, we do that by absorbing the photon. Now it's never going to reach that screen. I just created a new screen a little earlier. You can instead imagine other non-destructive ways of measuring it. But again, we know the uncertainty principle. We know that anything I can do to get good enough position resolution here is likely to disturb the momentum so much that it will change the pattern I see on the screen. So experimentally, this was yet another application of these weak measurement ideas, that we can measure on average where is the photon in this plane without disturbing it, let it continue along its way, and then ask, where is it later? If I found it here, where was it on average before? If I found it here, where was it on average before? And the motivation for this was actually a bit convoluted. One of the other things my students need to learn is that we cannot rule out hidden variable theories of quantum mechanics. Many people, when they're taught about EPR, are taught, we learned that there are no hidden variables. And that's not correct. We learned that there aren't local hidden variables, but in fact, since 1950, we've had a very good hidden variable theory that is predictionally indistinguishable from quantum mechanics due to David Bohm building on de Broglie's ideas. And it's a dualistic theory of nature. It has particle-wave duality explicitly and literally, meaning that there exists a wave and there also exists a particle, and the particle rides along the wave. So every particle has a definite position. And yet when you look at where the statistics of where the particles end, they end up being described by the wave theory. So there's an interesting question. Can you actually measure those Bohmian trajectories where a given particle went? And what Howard Wiseman, our common collaborator, realized, again, about 15, 20 years ago now, was that if you weakly measured the position of particles in this plane and then post-selected on where do they land in this plane, so you asked, on average, where did a particle here come from? And you find here, and you connect those dots. And then you do it again in the next plane. On average, where did the particle here come from? You connect those dots. You'd get many different trajectories depending on where you put that final selection. And they would agree exactly with the trajectories in the Bohm model. Now, that's not a proof that the Bohm model is correct. It's just an interesting connection between measurable reality once you understand weak measurements and these things in the Bohm model that people used to think were beyond the realm of direct observation. So it made it exciting to us that that was directly accessible. And that's what we actually did. A way that you can think about it without the metaphysical language in terms of things that sort of straight textbook quantum mechanical people know is that there's an operator in quantum mechanics that gives the flux, the number of particles per unit time traveling through a given region, or even what direction they're traveling in. And if I have a double slit wave function, maybe I can't ask exactly where is the particle, but I can ask at each position, what is the net flux? Where is the probability density moving as a function of time? And what we discovered is that we could directly measure that observable, and that observable is equal by construction to the momenta of the trajectories in Bohm's model.
So many people would say that Bohm's model is already supposed to be consistent with quantum mechanics. It's experimentally indistinguishable, some people say. So why would it be surprising that what you find is consistent with Bohmian mechanics? Wouldn't it also be correct to say it's just consistent with
Oh, I see.
Pick your flavor.
Right, sorry. So, of course, you're 100% right. At the end of the day, if we just measure where do the particles land on the screen, that's describable by straight quantum mechanics, or honestly by Maxwell's equations in our optical experiment, or by Bohmian mechanics because it was built to give the same answers. That's guaranteed. But Bohmian mechanics adds something else to the story. It talks about where each individual particle was along the way, building up these trajectories that we always used to think could not be directly observed. Only the statistics were observable. So to most people, us included, it was surprising that there was a direct measurement with a sort of clear operational motivation that revealed those so-called hidden trajectories of the Bohm model, not just the prediction for the final state.
Now, if that's true, do you think you, Professor Steinberg, can find a preferred reference frame?
I don't think it's directly connected to the question of a preferred reference frame. The question in relativity of preferred reference frames is a really interesting one. First of all, the universe has a preferred reference frame. There is a rest frame of the cosmic microwave background. So there is a clear sense in which it's preferred. The laws of physics happen to behave in such a way that they are the same in any other reference frame, just the state of the universe happens not to be. There's a really interesting article, again by John Bell, but on relativity, not on locality, and his theory, arguing that our usual university treatment of relativity emphasizes the relativity aspect too much and the equivalence of different reference frames too much. And he would point out that it's entirely consistent to think of there being a preferred reference frame, and that in some ways maybe that's a cleaner way to think about it. That said, you could pick whichever reference frame you wanted and call it preferred. So is it really preferred?
I guess where I was going is that Tim Maudlin, who is a reformed Bohmian or a Bohmian with an asterisk.
Is that what he is? I know Tim a little bit, but not well enough. Okay.
He may say, maybe I misread, or maybe I'm conflating someone else, that your experiment demonstrates is evidence for Bohmian mechanics, and in his view, there's a preferred reference frame. So that's where I was going with that.
Okay. So standard Bohmian mechanics, first of all, is non-relativistic. So it has a preferred reference frame because we didn't move beyond that. Other people since then have tried to relativize it, and we didn't use any of those more modern approaches. So in our case, there's a Newtonian preferred reference frame. Also, I'd be really surprised if Tim thought our experiment could give any evidence for Bohmian mechanics. I think he'd pretty adamantly say no experiment can give evidence for or against Bohmian mechanics without giving evidence for or against quantum mechanics, because they're operationally indistinguishable. You can imagine extensions of Bohmian mechanics that then deviate from textbook Copenhagen quantum mechanics. That would be different. I feel like experiments do more than just test a theory. Experiments tell you which elements of the theory turn out to be important for describing the situations we can really get into. And that gives you intuition for which aspects of a theory you want to ascribe reality to. It's not a proof, but I think it guides us until we can get something more like a proof, or at least, an Occam's razor. So I do think experiments like ours give more ammunition to the camp that says, no, you should think of these trajectories as being real. Doesn't prove that. You don't have to. I'm still not at all convinced that I do. I liked Bohmian mechanics a lot when I first learned of it. I learned about some of its predictions that were so strange. When I say predictions, again, I mean for these intermediate steps, what the trajectories are doing, that I said, I can't see that as a helpful view of reality. I'd be really surprised if that turned out to be the quote unquote right description. And then later on, I saw more that made me think, all right, maybe I was too quick to jump to conclusions and it's still okay. But I'm certainly not an adherent to Bohmian mechanics.
So I apologize, Tim. I didn't mean to put words in your mouth. I probably put words in your mouth. So those words are mine that I misremembered. I hope I'm remembering this part correctly.
Okay.
Did you go in physics in part because your dad asked you what an electron was and you couldn't answer?
Yeah, I did tell someone this story. There's some truth to it. My dad was an electrical engineer. And unlike me, he was very focused on practical issues that I only grew to appreciate decades later. And the story I told is of him teaching me about electric circuits when I was quite little. And I don't know, at some point he must have needed to explain to me why electrons flowed the way they did. And I remember him somehow alluding to the Pauli exclusion principle. The two electrons couldn't be in the same state at the same time. And all I cared about is knowing why that was true and where that principle came from. And I think I disappointed him in that I didn't let him explain the rest about his transistor to me, because I just wanted to know that. And he couldn't answer that question. And what I didn't know at the time is that neither could physicists. I mean, we can answer it mathematically, but why fundamentally? That remains the deep question.
Well, decades later, what have you learned? What would you tell your dad now?
What a great question. What would I tell my dad now? So there's a mystery in quantum mechanics about the treatment of indistinguishable particles, and that's where the Pauli exclusion principle comes from. And it's also where superconductors, Bose-Einstein condensates that we also work with in my lab, come from. And I don't think we have a very deep understanding of why it's the way it is. In 3 dimensions, we can show that particles have to either behave like photons and quote unquote like falling into the same state and condensing and making things like laser beams or superconductors, or they have to forbid any two particles falling into the same state and make sure that one excludes the other from that state. There's a theorem known as the spin statistics theorem that shows that this is fundamentally related to the angular momentum of the particle. I kind of think that the formulations I've heard of that theorem are almost a little bit circular. You have to assume something about the structure of field theory that I kind of think is as big an assumption as the conclusion of the theorem itself. That's often true. Theorems are often bidirectional, and it's a matter of taste. What do you consider the hypothesis, and what do you consider the conclusion? But fundamentally, if you buy the theorem, what it says is that particles with half-integral spin can't show up at the same place. They have to exclude themselves. Why are all electrons identical? Couldn't you imagine a universe that was just created with 18 billion electrons, and each one had its own serial number? That's not how it works. The way we understand that mathematically now is to say particles are really just excitations of a field. And there are many fields out there. And when I say there are 1 million electrons, what I mean is the energy stored in that field is 1 million units above absolute zero. And it's in that sense that the particles are truly indistinguishable. This thing about half-integral spin, though, when we learn quantum mechanics, one of the first things we learn is that angular momentum is quantized in units of Planck's constant. It can be 10 to the minus 34 joule seconds, or it can be any multiple of that. And then it turns out that the first particle we were worrying about, the electron, violates that so-called rule, and it has half a unit of angular momentum intrinsically. And you just need to accept that. And there's a real mystery about particles that behave that way. I think the way to sum it up is that normal objects, if you rotate them 360 degrees, look exactly the same as before you rotated them. There's a sense in which particles like electrons look like they've undergone a funny flip after you rotate them 360 degrees, and you need to rotate them 720 degrees to make them actually look the same as how they started. And it's that rotation that mathematically we call half-integer spin. It's that rotation that means if you have 2 electrons and you exchange them, you're doing something that's a little bit different from exchanging 2 photons or other particles. But like much of physics, it's something where we have the mathematical law, and we don't really know to this day what underlies it.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, TOE is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off.